Thank you very much. I'm sorry I caught a cold yesterday, so I cannot talk so well. And maybe I have to sneeze. So this is work with a lot of people, but maybe I'll mention them later. So Higab Ahn is in Postec, Sang-won Bae at Kyunghee University, Joachim Gudmundsen at the University of Sydney, Takeshi Tokuyama at Tohoku University, or whatever is left of it, and Antoine Vigneron is at King Abdullah University of Science and Technology in Saudi Arabia. So maybe you've heard about Kakeya's problem. So it's the question, what is the smallest garden in which you can turn around a ladder of given length? Let's say length 1. But to make it more interesting, maybe you want a ladder of length 10 meters. And the question is, how do you have to make the garden so that you can turn it around fully? Right? So you start like this, and you want to turn it like this. And this problem is rather famous because much later, Besikovic showed that, in fact, the answer is there is no such smallest garden. For any epsilon, you can make a garden of area less than epsilon in which you can turn around a ladder of length 10 meters. But that's not the version of the problem I'm interested in. I want to restrict my garden to be reasonable, something allowed by the government, so I want it to be convex. And here Pahl showed in 1921 that the optimum solution is an equilateral triangle where the height here is 1. Right? So this would be my ladder. And of course it's easy to see that you can, first you can turn it like this, then you can shift it down here, then you can turn it like this, and you can shift it over here, and then you can turn it like this. Right? And equivalently, you could ask the following question. What's the smallest area convex set in which you can place a ladder of length 1 with every possible orientation? So clearly, fulfilling this requirement automatically fulfills this one. The opposite is not so clear, but for convex sets this is true. So in this case, the two problems are actually equivalent. And in fact, the optimum here is also optimal if you only require this here. Right? So what is the smallest convex set in which you can place a unit length segment of any possible orientation? And that leads us immediately to this generalization here. If I give you a family of line segments, and I'm not requiring it to be finite, just some set of line segments in the plane, I want to know what is this convex figure of smallest area such that every segment fits inside P. And by fits inside, I mean every segment from this family can somehow be translated so that it lies in P. Right? So then Kakeya's problem is a special case where this family here simply contains all unit segments of every possible orientation. And now I want to know, well, in general, if these segments are not necessarily all possible directions, they're not necessarily unit lengths, what do you get? And it's usual to start with the easy case. So the case of two segments is very simple. You can just put the two segments anywhere you want. Right? So if I have these two segments, then I can put them like this and take the convex hull, or I can put them like this and take the convex hull, or I can in fact draw them anyway such that they intersect and take the convex hull. And the convex hull has the same area in all situations. Right? So as long as the two segments are touching or intersecting, the area is the same. So in particular, you can make it a triangle. Now for three segments, it's not so easy, but it's a nice little exercise that if I give you three line segments, you can always take two of them and translate them so that they touch at the corner. and then the third one will fit inside the triangle formed by these two. Right? So you can start with, you can pick two of the three, move them so that they touch at a corner, and then the third segment fits in the triangle. So again, the solution is a triangle. So trying something more complicated, if I come up with a set of line segments and a quadrilateral that contains them all, then you can always move one vertex of this quadrilateral and make it into a triangle without increasing the area, and so that you can still fit all the segments. So then again you can get a triangle. Well, and then of course we have Kakeya's classical case here, where we already know that the answer is a triangle. And so this led my co-author Higab Ahn to this, what I call the crazy conjecture, that the answer is always a triangle. So no matter what set of segments, finite or infinite, countable or uncountable, unit length or arbitrary length, he thought it's always a triangle. And I thought this was just ridiculous.
But, can you go back? The three segments you can always place. Third one fits inside the triangle they form, but do they form the smallest triangle?
Yes, because if you have two segments and you put them like this, then already there is no smaller set that contains these two segments. So this triangle is already minimal for these two segments. And no matter how you put two segments so that they touch, you already have a minimal set. Right? So the third segment is for free.
Is the same thing true for all segments?
I don't think so, but I'm not sure.
And it's conjecture is false?
No, so for four segments, I don't think it's true that you can take two of the four segments and make a triangle out of them. But as you will see, there is a triangle. It's just not clear that you can have two of the sides of the triangle to be the original segments. Right, so let's investigate this a bit more closely, and I want to introduce a function for this. So if I give you a convex figure in the plane, and I take a line of slope theta, right? So L theta is a line that makes angle theta with a positive x-axis like this. Now I take my figure C and I project it orthogonally on this line. Right? So then the projection here is an interval, and I measure the length of this interval, and I call it the width of C in direction theta. Now this I do for every possible direction, right? So this would be the width in this direction here. And so now I get a function. So for convex set C, I get this function WC, which maps the interval 0 to pi to the non-negative reals. Right? And so somehow this width, this function WC, I call it the width function, it characterizes the object, but obviously it doesn't characterize it uniquely. For instance, if I tell you that the width function is constant, it's equal to 1, there's one obvious object that has this width function.
You mean the Rouleau triangle?
Exactly, the Rouleau triangle.
Is it more obvious?
And there's another one, another well-known one, which is the circle. And in fact, you can interpolate between these two, and there's a continuous family. And those, in fact, are all the ones that fall in between here. And so if we go back to Kakeya's problem, we can actually reformulate it as follows. What's the smallest area convex figure that has widths at least 1 in every possible direction? Right? So it's easy to see that this is equivalent to requiring there's a unit length segment in every direction. Right? So the smallest area convex figure with widths at least 1 in every direction, well, and we know the answer is the triangle of height 1. Okay, so, and in fact, it turns out that this is a very productive way to look at this problem. So I'm trying to reformulate my problem also in terms of the width function. And to do so, I need this lemma here. Oh, it's a theorem. So if I give you a segment S and a convex figure, and I tell you that the width function of the segment is dominated by the width function of the polygon, sorry, of this convex figure here, it's not necessarily a polygon, then you can translate S to lie inside P. So this, I think, is surprising, because it's not true if it's for two convex figures, right? I mean, the unit diameter circle and the Rayleigh triangle both have constant width 1, and neither fits inside the other. Right? So it's certainly not true if you put convex figure P and convex figure Q. But I claim if you take a segment, then you can just test if it fits inside P by comparing the two width functions.
So you do it for every zeta, or when you compare?
Okay, so what this means is pointwise domination. Right? So for every theta, the widths must be less than or equal. Right? So when I compare two width functions, I always mean this pointwise. So I mean this statement here. Right? So let's try to argue why this is true. So let me take a segment S, and well, for simplicity, let's take a horizontal unit length segment, and I'm given an object P such that the width function of P dominates the width function of S. So which proof do I show you? Because I know two. Okay, so let's look at this object here. So we want to show that this one can be translated to lie inside here. So what's the most likely place to put it? Well, the most likely place would be if you sweep a horizontal line over this object to pick the point where this cross section here is maximized. Right? So do this. Take a horizontal line, sweep it over this object. So this will, the length of the cross section is actually a convex function, right? So it starts at 0, it increases, and then it decreases again. And at some point it has a maximum. So let this be the maximum. Now because the object is convex, the fact that it's a maximum means that you can place two parallel supporting lines here. And now I ask the question, well, what's the distance between these two lines here? Well, the distance would be fix this angle theta here and take the projection on this line here. So that means that this distance here, it's exactly the width of P in direction theta. But now I know that this is lower bounded by the width of the segment in direction theta. Right? So if I draw parallel lines for my line here, it turns out that this length here is less than or equal to this length. And that, of course, means that I can translate this guy to lie on here. Right? So this segment here is 2. So if you have a segment, then this implies that S fits in P. So let me record this for further use and tell you a new theorem, which I call the width theorem. So if I'm given a convex figure in the plane, then there is always a triangle T such that this is the area here. So the area of the triangle is at most the area of P, and the width function of the triangle dominates the width function of P. Right? So this is somehow funny because it says no matter what object you start with, you can always make it smaller, and yet the width function increases. And you end up with a triangle. And we will see that this statement here, so this theorem implies our triangle conjecture. Why? It's very easy now. Start with a family of segments and take a smallest area convex figure such that every segment fits in here. So here I need that such an object actually exists, but that follows from compactness reasons. There is a whole literature where they do this. I think it's called the Kneser compactness argument. And then, right, so I pick this convex figure here. Now I use my width theorem, which says that for this convex figure, there is a triangle whose area is at most the area of P, and whose width function dominates the width function of this P. Now I want to argue that every segment from my family fits in this triangle. So why is this true? Pick a segment. Well, we know it fits in P, but because that's how I choose P. So that obviously means that the width of S is bounded by the width of P. Right? Otherwise it wouldn't fit inside. But now we know that the width of P is dominated by the width of T. Right? So we have that the width of S is bounded by the width of T. And now I use this theorem here, which tells me that S fits in the triangle. So I got this fact. So this proves the triangle conjecture. For any family of line segments, you can always choose the smallest area convex figure to be triangular. So it remains, of course, to prove the theorem here. So how do I do that? So again, I need a tool, and this tool is called the Minkowski symmetrization. It's an extremely useful tool to know if you do any kind of discrete geometry in the plane, or even in higher dimensions, because it has all kinds of useful properties. So if you start with a convex figure K, what you do is you take a mirror image of K, so you mirror around the origin, and then you take the Minkowski sum of these two, and then just for convenience you scale it down by a factor 2. Or written differently, you take all these vectors here where x and y are elements of K. So let's do an example. So if you take, let's say, a triangle like this, and now I take the mirror image, so let's say the origin is here, so then this point goes here, this point goes here, so this would be the mirror image, right? So this is K, this is minus K, and now you take the Minkowski sum, which means I slide this around this one, so I would get this object here. So you get a hexagon. And now I have to scale it down by a factor 2. Right? Another example, if you start with a rectangle, the mirror image is a rectangle, and if you take the Minkowski sum, you get again a rectangle. You scale it down by a factor 2, and what you get is the original rectangle. So if your original object K is centrally symmetric, you simply get the object itself. Right, and so we easily observe that this object K bar, the Minkowski symmetrization, it's centrally symmetric around the origin. That's why it's called the symmetrization. Right? Simply because if x and y are from K, then y and x are also from K. The width function is the same as for the original object. And that simply follows because the width function is periodic with with pi. Right? So if you take this Minkowski sum, you're kind of adding the widths of k and minus k, but that's the same. And if you have two objects whose width function is the same, then their symmetrization is the same. This shows you, for instance, that the symmetrization of the Rouleau triangle is what? A circle, right? Because the Rouleau triangle has the same width function as a circle, and so its symmetrization must be the same as the symmetrization of the circle, but the circle is its own symmetrization, because it is already centrally symmetric.
But is that the third property, is it obvious to see, or?
This one here?
Yeah. Or is it
It follows from this one here, and this is not difficult to see. Right? So, as I said before, in general, we cannot argue that if one width function is dominated by another, that one object fits inside the other. But for these centrally symmetric around the origin object, this is true. Right? So if I tell you that the width function of P dominates the width function of Q, then the symmetrization of P actually contains the symmetrization of Q. And it's actually not difficult. So if you assume that this was false, so assume you have, assume it's not true, so that would mean that Q, there must be some point Q which is in Q bar, but not in P bar. Right? So you have this object P bar, and a Q which is in Q bar, which is not inside. Right? But then, because this object is convex, there is a line that separates this one from this one. But now by symmetry, if you mirror this line, it will separate this object from Q, from the opposite of Q, right? From minus Q, which is of course also in Q bar. And now you get that the width of P bar in this direction is less than the width of Q bar, which contradicts your assumption. Right? So this part is easy to see, and if you apply this twice, you get this. I need to learn to put the chalk where it cannot roll down. Okay. So my width theorem somehow, it was about the question, I'm given a convex figure, and so it has this width function. Now what I want to do is I want to minimize the area while dominating this given width function. Right? So I could ask this question here. If I have a convex figure P, what would be the smallest convex figure whose width function dominates my given width function? Right? And well, now a natural different question to ask is, well, if I'm given a convex figure, what would be the smallest figure that has exactly the same width function? So for instance, if I tell you that my width function is constant 1, so maybe P is a circle, what is the answer to this? The Rouleau triangle again, right? Because all the figures whose width function is constant 1 are exactly the Rouleau triangle, the circle, and the interpolations. Right? They are weighted Minkowski sums. And the Rouleau triangle is the one with minimal area of those. Right? Because of the isoperimetric inequality, of course. It can't be the circle. Right? And of course this one I can rewrite by saying, given a convex figure, what's the smallest convex figure such that they both have the same symmetrization? Right? As we just saw, this statement and this statement are the same. Right? And now it turns out that this question has been answered by G.D. Kakeya in 1966 in an obscure paper whose abstract does not include the statement, so I was extremely lucky that I found it. So he proved that among the smallest area convex figures there's always what I will call a trigonal disk. He used a different name. He called it the relative Rayleigh triangle because he thinks about it as a Rayleigh triangle in some kind of Minkowski plane. But I'm using this term here, which is coined by KAIST Theorem. So a trigonal disk is a convex object which you can sandwich between a triangle and a centrally symmetric hexagon. Right? So you start with a hexagon AU, BV, CW. It's centrally symmetric around the origin. So V is actually minus A, U is minus C, and W is minus B. And then the trigonal disk must be sandwiched between the triangle ABC. So it must contain ABC, and it must be contained in the hexagon. Right? So this is called the trigonal disk. And the proof is actually very elegant. So he uses the fact that if you have a convex figure K, then it is always possible to find an affine regular hexagon inscribed in K. And by inscribed it means it actually touches K with all its 6 corners. I guess I want this to be centrally symmetric. Right? So there is something that looks like this. Right? And so this hexagon is not only centrally symmetric, but it's actually the image of the regular hexagon under an affine transformation. So for instance, that says that this side must be parallel to this and half the length of this one. Right? And now what I can do, or what Kakeya did, was to pick one of these 3 triangles and attach to it this arc and this arc. So you move this arc here, and you take this arc and you move it here. And then you show that the symmetrization of this object is exactly the original K. Well, you have to scale by factor 2, obviously. Right? Because the symmetrization of the triangle will give you this hexagon, and these pieces here, somehow they magically appear in exactly the right places if you do the symmetrization. So this one shows up here, and it will also show up here. This one shows up here, and also shows up here. And the object, of course, is a trigonal disk. And then, of course, you have to show that this is actually the best you can do. And that part is not so easy. Okay, so now let me get to my width theorem. So let me remind you. I want to show the following. For any given convex figure, there is a triangle whose area is at most the area of the original object P, but whose width function dominates the width function of P. So I pick a smallest area figure whose width function dominates P. And by this result by Kakeya, I know that I can choose this to be a trigonal disk. So there is a trigonal disk D whose area is at most, well, the area of P, and whose width function is identical to this one here. Well, I guess I could just have said I can assume that this is a trigonal disk. Right? No, Kakeya proved it for equality here. Right? So we have to do it in 2 steps. So first I pick this one here, the smallest area figure that dominates this. Now Kakeya tells me there is always a trigonal disk that has the same width function and whose area is not more than the area of this one here. So that tells me that actually I can choose this one to be trigonal. Now I want to show that for any trigonal disk, I can actually replace it by a triangle without increasing the area and without decreasing the width function. So let us do that step. So let me draw an interesting object, maybe like this. So this is a centrally symmetric hexagon. Now I draw this. No, let me draw the triangle like this. So this is A, B, C. So my trigonal disk somehow has an arc here, and an arc here. Now what I do is I choose a line, I choose a tangent to the trigonal disk parallel to this line here. Right? So I would draw this tangent here. And I measure the distance between these two lines vertically, like this. Now I copy this distance up here and choose a new point C prime here. And I take the convex hull of the original trigonal disk and I cut off this arc here. So I use this object now, like this. Now first of all, let me call this D prime, if the original was D. So now, first of all, this object has not larger area than D, because the area we lose here at the bottom is more than the area we gain at the top. Do you believe it? The reason to see this is if you take this point here and you draw this triangle, and you take this here and you take these two triangles, then this triangle has larger area than these two. The areas would be exactly the same if these 2 points are here. So if the result is a triangle, then this triangle and these two would be exactly the same. Right? So the area of D prime is not more than the area of D. Now what about the width function? Well, if you take any two lines, two parallels tangent to the original D. And now we have to check how these parallels have to move when we replace D by D prime. So they can only move, of course, or the only problem could be if I'm touching on the bottom here, right? Because that's where I'm losing something. So if you take a tangent like this here, this would move up a little bit. Right? But now the interesting property of trigonal disks is that for any tangent on this bottom arc here, the parallel tangent must go through this point C. Right? It follows from the fact that we are inscribed in this centrally symmetric hexagon. And so that means that now when I move this line up here, it can move at most by this distance. But here I move at least by this distance. Right? So the width that I gain at the top is definitely at least what I'm winning at the bottom. And so that gives me that the width of D prime dominates the width of D.
So how Why did you choose that direction?
Which direction?
The one that you're adding a point at the top, the little red arrow.
This little red arrow?
Yeah.
So this is parallel to these two sides. Right? So I've drawn the hexagon with these two sides vertical. And so what have I done now? I've replaced the trigonal disk by a new trigonal disk d prime, while not increasing the area and while not decreasing the width. But what have I gained? What I've gained now is that one of the three chords of this disk is actually a segment. So I can repeat this process 3 times and I get a triangle. Or I could put it differently. I could always say here, let me choose a trigonal disk that has already the maximum number of straight sides. And then if it wasn't a triangle, we get a contradiction. Right? So this
maximum number of straight sides. You can use that only if there's only finitely many.
Yeah, but the trigonal disk has only 3 chords, right? So a trigonal disk is kind of a generalized triangle. It has 3 convex arcs that merge at these special outer corners. And among the trigonal disk, I can count how many of these arcs here are actually straight segments. Right? It could be 0, 1, 2, or 3. And here I could just say, let me pick a trigonal disk that maximizes the number of straight segments. Now let me assume it's not a triangle. Well, then we use this argument and derive a contradiction. Right? Because if it's not a triangle, then it has one of these arcs, but this one I can doctor away, and the new one will have one less. Okay. So this proves the width theorem, and therefore, as we have seen, it proves this this triangle conjecture.
So can I ask something?
Yeah.
So the end triangle maybe has, the edges don't have to be parallel to these original edges of this hexagon. Is it true?
Not of the original one, right? So.
I mean, yeah, things could change.
Yeah,
now
because
I'm going to add another point outside A.
Yes.
Now I made that one edge and it's there, but then I add this point and. Okay.
That is right. Yes.
So directions
Yes.
can change.
Yes. 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 Okay. So this proves the conjecture. The optimum can always be chosen to be a triangle. But, well, how did we actually get at this problem? We wanted to solve an algorithmic question. So if I'm given a set of line segments, how would you actually find this optimal set? Previously, we found this question quite hopeless, but now that we know that it's triangular, it should be much easier. And in fact, it turns out there is now a very simple algorithm. Given a set of n line segments, finding the smallest triangle such that all the segments can be fit inside. What you do is you simply translate the segments so that their center is at the origin. Then you take the convex hull. This gives you a centrally symmetric convex figure. Now you choose the smallest area affine regular hexagon circumscribed to this figure. And then you return the triangle whose symmetrization is this hexagon. Right? We have seen here that the symmetrization of a triangle is a hexagon. It is in fact an affine regular hexagon. And so if you have an affine regular hexagon, there is always a triangle that generates it. Right? You just draw these, you partition it into 6 pieces, and then you pick this triangle. And that's the one you need. Or in fact, that one or that one. There's always 2 solutions, of course. One the mirror image of the other. And why is this correct? It's correct because what we want to do, we want to find the smallest triangle such that the width of the triangle dominates the width of some original set. Now this, if you look at this set here, the way I've defined it, its width function is simply the maximum of the width function of the segments. Right? Because I've constructed it by putting all the segments at the origin. Whenever you have a pair of parallel tangents, they are defined by one of the segments. And so the width of this object here, in every direction, it's defined by one of the segments. And so this is simply the pointwise maximum of this. So when you're looking for another object that dominates all of them, well, then it must dominate the maximum, and that means it must dominate this one here. Right? So we are looking for the smallest area triangle whose width function dominates this one here. But that means that its symmetrization must contain the symmetrization of this one here. This one is already symmetric. The symmetrization of a triangle is an affine regular hexagon. So we are looking for the smallest area triangle whose symmetrization is circumscribed to P. And now we simply need the fact that there is a constant factor between the area of the triangle and the area of this hexagon. So instead of minimizing the area of the triangle, we can just as well minimize the area of the hexagon. Right? So minimize the area of the hexagon automatically gives you the smallest triangle into which you can fit all the segments. And now, of course, all that needs to be done is this part here. Given a centrally symmetric 2n-gon P, find the smallest area affine regular hexagon. And that's where computational geometry comes in, and the other three authors, because now you need to prove some properties of what this looks like, and you have to come up with an efficient algorithm. But since this is a discrete math seminar, I will not bore you with these computational details. So the key is to prove that this object actually must share either a vertex with P or it has an edge parallel to an edge of P. This is not trivial. It took us quite a while to prove this. But once you have this, then getting the algorithm is not difficult. And that ends my talk.
Do you have any questions?